Aloha class section 4.6 related rates, the last section in chapter 4. So we're going to test it up here pretty soon. And guess what? Homie came to hang out with me and help me do some related rates problems for you. What's up? Hello. Aloha. All right, here we go. Warm up. A skill that we're going to be able to have to do is do things implicitly here and dealing with different variables, which messes some of us up. So I'm going to do A for you, and then what I want you to do is take a stab and see if you can find out how to do B on your own. Okay, so they want me to use this function right here, y equals, and my marker's not working already. Come on, homie. Be right back. All right, class, let's see if it works now. Come on, help me out. dy du is equal to the derivative of 2u, which would be 2 du, right? And we usually don't write the du. So it would just be 2. But for the p, the derivative of p would be 1, but then I have to add the dp du because I'm really doing the derivative with respect to u. And my last one would be t to the 1/2, which would be 1/2 t to the negative 1/2. But since I'm supposed to be doing it with respect to u, I have to add the dt du. All right, hit pause. Try that bad boy. Okay, I really hope you did it. That's the only way you're going to get good at AP Calc. Derivative of 2u would be 2 du dx, because it doesn't have an x, plus 1 dp dx minus 1/2 t to the negative 1/2 dt dx. All right, let's keep on rolling now, okay? Related rate problems. You use related rates when the problem asks how fast a quantity changes. How fast a quantity changes. Okay, class? Related rate problems fall typically into 3 categories. The Pythagorean theorem, right triangle trig, known or given form, really anything you learned in your geometry or pre-calc days. All right. Be sure to always use correct units when dealing with related rate problems. For example, if h is measured in centimeters and t is measured in minutes, when I find dh dt, that's going to give me a unit of centimeters per minute. Thus, that's how fast something is changing. Let's get after this already, right? Example 2. Now, you guys know I don't always like these worksheets. I kind of give you these step-by-steps. Okay, so I'm going to kind of go through it, but I don't like the step-by-steps. Okay, I'm going to tell you how you should attack them in class. Let's say we got Tweety or Homie hanging out in some birdhouse. Okay, so we got some cool birdhouse up there, and he's hanging, and that's 24 feet off of the ground. All right, and then we got our boy Sylvester, not a cool dude, that's got some ladder that's trying to get Tweety or Homie up in that box, and we'll say that's 26 feet. Okay, so whenever you're doing these problems, what you want to do first is just read the problem. And whenever they're giving you a situation, it's always good to draw it. Okay, it's always good to draw. And maybe you have as good drawing skills as Homie and myself. Okay, all right. So we got 24, we got 26. I don't technically have anything down there yet. Okay, but we got Hector the dog that starts pulling the base of the ladder. So we got this cool little dog here, and he's pulling that ladder away. And he's pulling that ladder away at a rate. So I've got to write something down for that. Well, I've got nothing here, so I'm just going to call that, we usually call that the x-axis. And it's a rate, and it's always with respect to time, right? Because it says feet per second. So I'm going to write dx dt is equal to 2. Okay, let's write down some other things that might be helpful. We have y is 24 when we start. Okay, so when time is 0, your y is 24. And then I'm going to call that c, because that kind of looks like a hypotenuse. We're going to call that 26 feet. So one thing you want to do when you're doing these problems is draw a picture and just start writing down some variables of what they would represent in your picture. And hopefully we're going to get some type of geometric formula that this relates to. Okay, how fast is the ladder falling? Well, we called 24 y, so it's asking me, I'm going to put a little star. It's asking me to find dy dt, right? Because they're asking me how fast that ladder is falling down the wall. And we called that y earlier. We called this c earlier. Okay, and they're asking me what's dy dt when y is equal to 10. So I like to put a star at what I'm trying to find in terms of a rate. And I like to write down the moment in question, we call it, when the ladder is 10 feet off. And I star this guy, I circle this guy, because the biggest mistake we made in AP Calc is we use that information before we are supposed to. You only use that information after you find the derivative. Boom. Okay? All right. We got everything we need, right? I wrote down every piece of information. 24 was written down, what it represents. That's just when we start. So that's probably not going to be too important. 26, we wrote that down, 2 feet per second. Ooh, I wrote down what I'm trying to find, and we got 10. So let's get after this bad boy. Let's start this problem. Okay? Is there a geometric formula that comes to mind with this picture? Oh, snap, that's probably a right angle. That would be Pythagoras, right? Pythagorean theorem, right, class? So let's write down what the Pythagorean theorem is. That would be x squared plus y squared is equal to c squared. Okay, and I don't want to plug anything in there yet because I haven't found the derivative. Biggest mistakes you guys will make. Don't plug anything in until after you have found the derivative, okay? So let's go ahead and find the derivative. That'd be 2x. And I'm going to find the derivative implicitly because all of this is related to time, right? So it's dx dt plus 2y dy dt equals 2c dc dt. Okay? And then I'm just going to go ahead and start substituting some stuff in. Okay, I got 2. Do I know what x is? Let's think about this. Do I know what x is? Well, I did a rate, so that means it's the moment in time. So I'm going to cross that out and say that's 10 now. Okay? So do I know what x would be? Well, AP loves doing this stuff. That's a triple, right? That's a 10. That's a 26. So what would x be, right? Because my boy Hector is pulling that away. Well, that's a 5, 12, 13 triangle. So if that's 5 times 2, that'd be 12 times. Oh, so it's 24. How about that? I kind of did the Pythagorean theorem just to get that. Or know my triples. And the AP loves using triples. It's kind of how you know you're off and you're on the right path. Right, Holmes? Okay? And then dx dt. Well, what's dx dt? Shame on me. I did right there. That was feet per second. Right? Dx dt was 2. Okay? And then we have plus 2 times y. What was y? Y at the moment in question was 10. Dy dt, I don't know, which is okay because I'm trying to find that. Right? Is equal to 2. C is 26. And what's interesting about that ladder is, and don't you dare, it is not one of those ladders, homie, that just can change. Okay, it's a ladder that's fixed. All right, so that's still 26. And if it's still 26, guess what? That ladder cannot change. If that ladder cannot change, it has a rate of change of 0 with respect to time. So that's awesome because that guy goes away, right? And then we get, what is that? There was that 2, that's 48, that's 96 plus 20 dy dt. And if I solve for dy dt, I get an answer of negative 96 over 20. And it would be my y is feet and my time is seconds. And then you just want to make sure, hey, did I answer the question? And I sure did. And here's something very important to realize, that this x of rate, that x is getting bigger, right? It's getting bigger. Thus, it was a positive rate. Very important. This started at 24, remember, and that got smaller. The ladder ended up being, it'd be like way out there, right? And that distance of y is getting smaller, thus the negative rate. How interesting. Now it's your turn, but actually what I want you to do is do this one with me, okay, class? And then what I want you to do is try some of these worksheets before you come into class, okay? Bugs and Daffy. And see, I like this example already better because it doesn't have the little steps for us, okay? Bugs and Daffy finished their final act on Bugs and Daffy show by dancing off the stage with a spotlight covering their every move. If they are moving off the stage along a straight path, so let's say we got these dudes, they're chilling, they're dancing it up, there's 2 of them, and they move off that path. Okay, I'm going to call that x, and I'm going to call that dx dt, okay, is equal to 4 feet per second. So that's done. And the spotlight is 20 feet away. So the spotlight, let's make that spotlight, I'll call that Y. That's 20 feet away. So you got some cool, big, huge spotlight. Okay, spotlight. What is the rate that the spotlight is rotating when they are 15 feet from the path, from the point on the path closest to the spotlight? Okay, so we're 15 feet. So at the moment in question, right, that's going to be my little star, is when we're 15 feet from that point of path. And if you look at this thing, what we're trying to find is the rate that that spotlight is rotating. And you know what's so important? Oh, and let's write that. That's also a moment in question. That's d theta dt is what we are trying to find, okay? And if you look, that distance is getting bigger, which tells me my final answer better darn well be positive. Now, this is going to be some tricks, so this is going to maybe cause a little bit of trouble. Well, let's think about this. Some people might say, oh, that's a Pythagorean theorem because I got a right angle. It's also a SOHCAHTOA, right? And why would I think SOHCAHTOA? Because an angle is involved, okay? So the question is, do I use SO? Do I use ka, or do I use toa? Let's think about this. Actually, hit pause and think real quickly. What would make the most sense? Okay, you know what makes the most sense? That's my angle. Okay? What is that guy right there? That is called the opposite. They gave me the adjacent. They didn't give us anything about the hypotenuse, so who cares about that bad boy? So which one of those trig functions has opposite and adjacent in it? It is tangent. So let's write a little relationship out about tangent. So we have the tangent of theta is equal to the opposite, which is x, divided by the adjacent, which is y. In class, did I find a derivative yet? No, I didn't. So that means you don't plug anything in yet. Okay, now if you remember last class, I said, don't you plug in anything until after you found a derivative. Well, I want you to look at this. There are three unknowns in that bad boy, right? You got theta, you got x, you got y. Okay, now I'm going to use a technique here that's going to save us a lot of time. Okay, but I don't always like saying this because people will do it when they're not supposed to. But I'm going to challenge you here. Really make sure you are listening. And then we're going to do a technique that's going to enable us to not have to do this quotient rule, which makes the problem really, really tough and long. Okay, and that is there's one number in this problem that's never going to change. Can you think of what number that is? 20. That's never going to change, right? This changes, the angle changes, but that y equals 20 never changes. Guess what that means? That means I can use it from the beginning. So we're going to do that even before we found the derivative. Mr. Tanaka, you said never to plug anything in. Okay, I like to use that rule when you first start these problems, because if not, you guys plug things in way too early, okay? Here going forward, you can do it if you're 100% certain it never, ever, ever changes, okay? And so here we go. Now that I've got my little equation here, which is nice, and I wouldn't want to do a product rule there, right, class? So let me write it even another way, and we're going to write that as 1 over 20 times x. Okay, now let's go ahead and find the derivative of that bad boy, and the derivative of tangent theta is equal to secant squared theta. But remember, everything is with respect to time. Okay, and then we have 1 over 20x, so that'd be 1 over 20 dx dt. Now, since I found the derivative, let's plug some stuff in and see if we can get an answer for this, okay? We have secant squared of theta. What? I don't know what d theta dt is, right? Because that is what I'm trying to find. But I do know what x is. Oh, I can't even put an x in anywhere. How does that help me out, homie? But I do know what dx dt is. So I can put a 4 in there. Oh, sweet, that becomes a 1/5. Now, you are really stuck because we have to get this d theta dt by itself. But how am I supposed to do that if I don't know what secant squared of theta is? Well, it's the moment in question, and I'm going to draw it right here. Okay, the moment in question, what's going on? Well, that's 20. Well, that's 15, right? That's my theta. And at the moment in question, I can use any of that stuff, right? I found the derivative already. Well, that's a 1520. And oh my gosh, what is the hypotenuse? And why would I need to know the hypotenuse? Because guess what? secant is really cosine, right, class? It's just the reciprocal. So I could actually find this value if I knew secant, cosine. Oh, cosine, I would need to know the adjacent and the hypotenuse. I definitely know the adjacent, it's 20, but what the heck is the hypotenuse? That's a 3, 4, 5 triangle. 3 times 5, 4 times 5, 5 times 5. So that's 25. So cosine of theta, class, would be equal to the adjacent over the hypotenuse, which reduces to 4 over 5. So guess what? Secant then would be 5 over 4. But what do I have to make sure I do? I have to make sure I square that bad boy. And that is equal to 1/5. And so that means d theta dt is equal to 1/5 times, what would that be? That'd be 16 over 25, right? So if I do my simplification, I get d theta dt, which is equal to 16 over 125. Whoops, shame on me. It's theta. Theta in AP Calc is always in radians. So it'd be radians per, what we say earlier, it'd be per second. And so that is my answer to the question. All right, here we go. We got one more. Okay, and the goal, right, class, is we get these guys done in 25 minutes. Here is the most important problem. You will see it as at least a multiple choice question on your AP exam. Okay, a water tank has the shape of an inverted circular cone with a base of radius of 2. So it's got a radius of 2. I'm going to use my picture right here to draw on it. And it has a height of 4 meters. Okay, so that's the cone. If the water is being pumped into the tank, and I should write out stuff, right, class? So we have a radius of 2, and this is the cone. Important to write that out. Radius 2, okay, a height is 4, and once again, that is for the cone. If water is being pumped into, if water is being pumped into at a rate of 2 cubic meters, that kind of sounds like a volume, right, if it's cubed? So I'm going to write dV dt, right, because it's a rate, says rate right there, is equal to 2. Now the question is my rate here, and this is where these get tricky, is that a positive 2 or a negative 2? It's a positive 2. Why? Because the volume is being pumped in. It's getting bigger and bigger. So let's put a plus sign there. This would be the moment in question. Can't use that till we find a derivative. And we want to find the rate at which the water level is rising. So water, that's usually called H. So we'll go dH dt. But I want to make sure I recognize that that's for the water. What is that answer? That's going to be positive because water's getting bigger. And we want to know when the water is at 3. So that's a big start here. You can't use any of that stuff. The volume of a circular cone. Oh, snap, they give it to you. Ghetto. All right, so let's write that out. Okay, you need to have that memorized. I'm not giving it to you on a quiz or a test. Got that, Holmes? All right, so this is kind of tough here because there are way too many variables to deal with. Okay, class, you have to do like a crazy product rule there. That just would not be fun. So what we're going to do is we're going to see if there's a way to eliminate one of those variables. And guess what? I actually can, and I'm going to do it in blue here. Okay, let's just, I'm not even going to find a derivative. Okay, I'm not even going to find a derivative. What happened? What is going on? Let's get back here. Boom. Okay, phew. I almost thought I lost you guys. I lost my train of thought. We're not even going to find a derivative. We're just going to find a relationship to hopefully eliminate one of those variables. Okay, I have my cone. My cone is 2. My height is 8. My height is 4. Okay, and those are fixed, right, class? Well, if they're fixed, we're allowed to use it. And then you got your water that's in that cone, right? And the water is R by H. Okay, so I'm going to use the 2 and I'm going to use the 4. Why am I allowed to use it? Because those things are never going to change. The R and the H I'm going to keep as R and H because those are changing, right? The radius of the water is going to always be changing and the height of the water is always going to be changing. Okay, and I'm going to write a relationship between it, right? The water, R over H, will be equal to 2 over 4. Oh, snap, how about that? R over H is equal to 1 over 2. Boom. So I'm going to use that relationship. Now the question is, do I want this equation up here that's in red? Do I want the equation up here in red? Do I want that in with all R's in it? or all H's in it? Guess what? It's kind of a simple question. Look at what you're trying to find. What are we trying to find? What is the question asking, Holmes? The question is asking, hey, what is dH dt when H is 3? So if that's the case, that means I want that to all be H's. Well, if I want that to all be H's, let's solve this for R, which means just I get 1/2 H. Okay, and then I'm going to come back up here, and in my equation, I'm going to substitute in that 1/2 H for R, okay, square it, and if I do that simplification, that would be 1/3 pi, 1/4 H squared, and another H, which gives me 1/12 pi H to the third. Now that's going to be so much easier to deal with, and guess what? I'm going to have to erase a lot of this stuff, you guys, so I hope I don't lose you. I just want to erase. Hopefully you guys have it in your notes. This sounds like so fun because it takes forever. What is it, 1/12? Ooh, you guys help me. I have nobody at home. Holmes, what is it, Holmes? It was 1/12 pi H cubed, and it's V equals. Okay, so once we have our equation, what do we do, everyone? We find the derivative. All right, so what would be the derivative of dV dt, right? Because it'd be 1 dV dt is equal to, that's H to the third. That 1/12 pi is just a constant, so I drop that 3. I get 3/12, which is technically 1/4 pi H squared dH dt. Now, the interesting thing is you work so hard just to get a equation in terms of H or R, depending on what we're trying to find, that people plug in things way too early in this problem. Okay, now I'm allowed to plug things in, though. That's a 2. That's a 1/4 pi H. What is H? Oh, I can use that now because it's the moment in question. I found the derivative. That's 3 squared dH dt. And then, believe it or not, I'm done, so. Okay, so let's go ahead and simplify. What would I get? I would get 2 equals, what would that be? That'd be 9/4 pi dH dt. Okay, get dH dt by itself, and I get an answer of what would it be? I get 8/9 pi, right? For show. And then I just have to be careful. H is meters. Okay, so that's meters, and time is, what was it? It was minutes, so it'd be meters per minute. Booyah! Dunzo! That is related rates. How fun. Do a couple of examples right now and come to class ready to go, because I'm going to have a brand new worksheet for us to do in class. Practice this stuff. Done in under 25. Homie says peace. I say aloha.